Section 14.7, Extreme Values and Saddle Points. So some things that you should be able to know, be able to do by the end of this section is you should know the definition of critical points, be able to compute and classify our critical points, and be able to find global mins and maxes on closed bounded domains. Okay, so before we get to the Calc 3 multivariable calculus version of all this stuff, let's just have a quick review of what happens with critical points in one dimension. What are critical points and why do we care about them? So in one dimension, of course, critical points are when you have f prime of c is equal to 0 or f prime of c does not exist. Why do we care about critical points? Critical points are coming from the section of the book that's discussing how to find max and min values of a given function. So to find max or min values of f of x, check critical points or endpoints of the interval. And so let me just draw a little graph here. We have some function. Okay, so here is our function f of x here. Where is the derivative equal to 0? Where the tangent line is horizontal. So right here, we have the derivative at that point is equal to 0. Also down here we have a cusp, and so at this point, so this is f prime of, let's call it c1 is equal to 0. Down here f prime of c2 does not exist. And we can see this gives us both so this is a local max, this is a local min, and they both happen to be global max and global min here. Okay, so And just to remind you, so when we say local max, local min, f of c1, let's say here, is larger than f of x for all nearby x. f of c2 is smaller than f of x for all nearby x. So this is a local min. Okay, so this is all in one dimension. This should all feel very familiar to you. So let's start doing the multivariable calculus 251 stuff. So here's a definition. Let f of xy be defined on a region R containing point A comma B. Then f of AB is a local maximum value f if f of AB is bigger than or equal to f of xy for all AB in some disk centered on AB, some open disk, I should say. Again, it's the idea for f of AB is bigger than f of xy for all xy close to AB. F of AB is a local minimum value of f if f of AB is less than or equal to f of xy for all AB in some open disk centered at AB. Okay, so this should feel very unsurprising. It's what we would expect the definition of a local max and local min would be. So now we want to be able to say, well, so if you remember, let's go back to, this one over here. Know the definition of critical points. We'll get to critical points in just a moment. We want to be able to compute and classify them. So how do we find these local max and local mins? Well, there is a very unsurprising theorem 10 here, first derivative test for local extreme values. So if f of xy has a local max or min at an interior point AB of its domain, and if the first partial derivative exists there, then the partial derivatives both have to be 0. And so this is perhaps what we would expect here. So in one dimension, f prime of c has to equal 0. Well, this is 251 now. We can't just say f prime of c or something like that. We have to talk in the language of partial derivatives. And what we need to guarantee here is that both partial derivatives, the x partial derivative and the y partial derivative, are 0 there if we have a local max or a local min. And so, this is the first derivative test, so we'll be using this later on in the section. And to kind of wrap up the video, let's get this first definition, what was actually my first bullet point here. The definition of critical points. An interior point of the domain of a function f of xy, where both the partial derivatives fx and fy are 0, or where at least one of the partial derivatives do not exist, is a critical point of f. And let me see. So again, this is the corresponding definition to critical points in one dimension. Derivatives equals 0 does not exist. Well, now we need, assuming the partial derivatives exist, now we need both partial derivatives to be 0. So in future videos, we'll be crunching through problems of this sort, but we should already be able to see an outline for how to attack this kind of problem. What do? You calculate, if I say find the critical points of some function, x comma y, take the x partial derivative, take the y partial derivative, set them equal to 0, and solve, which is the natural generalization of what we did back in Calculus 1.